Hello everyone, this is Rohit Maurya and I'm going to start Unit 4 of the subject Introduction to Solid Mechanics. And fourth unit is about to find the slope deflection of different type of beams under loading. And the another part is the struts, various types of curved beams. So we're going to start from the calculation of deflection of beam by different methods. So let's just start it. So first part is to drive equation for a curved beam. So to find particular equations due which we can find slope and deflection on a loaded beam. So here it is. If a beam is subjected to pure bending, let's just start with the diagram. Here it is. So as we can see that there is a beam deflected which is under loading, and we cut a part PQ. Okay, and this deflected shape of beam is also called as elastic curve. So to find a particular equation that which describe how the behavior of this elastic curve can also be analytically analyzed, the slope and deflection of this beam. So what did we do? We cut a section of this elastic curve PQ and analyze this part. So by analyzing, we assume that the diagonal distance, or we say our distance in arc of PQ is ds. Let's just assume that PQ distance is ds, and the arc which is created by this elastic curve having angle which is d theta, and the radius that accumulated by this arc is capital R, and this PQ diagonal has a theta angle with the x-axis. Then let's just analyze this curve or arc, or say arc. So how can we do that? PQ, we made a triangular which is here, and DF shows a diagonal distance of PQ. Okay, DF shows the diagonal distance of PQ, and if we put a line P parallel to the x-axis which is denoted by DE, and we put a vertical line from Q by y-axis which is denoted by EF, then we consider a triangular which is called DEF, into which we have a distance ds, dy and dx, and then we try to solve this triangle which having a angle theta which is shown in here. Okay, then by analyzing this triangle we create some slope equation. We can deduce the value of ds. We also can deduce the one relation which comes from this triangle. We can find the value of ds in terms of r and d theta, which is directly, we can say that r into d theta is equal to ds, which is a formula of arc which already been shown here. Okay, which is shown here, ds is equal to r into d theta, and according to this triangular, as you can see here also, the tan theta is equal to dy upon dx, which comes from this diagram, or can say from this diagram. Let's get a little further. Here it is. We know that tan theta is equal to dy upon dx, and just after that we differentiate with respect to x, and we get the value sec square theta d theta upon dx is equal to d2y upon dx2. and further we did put the value of d theta, which also been uh, calculated or say uh, put, which is as follows: d theta is equal to ds upon r. We can find with this formula or this relation. We put the value of d theta here, and we have ds upon r, and 1 upon dx is equal to d2y upon dx square. Okay, we also know that ds upon dx is equal to sec theta. We also know that from which figure? From this figure. If we divide ds by dx, then we have sec theta, which is shown in here, and put the value of sec theta in here. Then we have sec cube theta upon r is equal to d2y upon dx2, which is here. Okay, let's get a little further. We have this relation, and we know that, as you can read out it here, usually r is very large as compared to beam span. Okay, and then tan theta or dy upon dx, the slope of the tangent to the curve at any point, is extremely small. So neglecting this term, what they are saying is the term theta, which is also b, it is very small in compared to the radius r. So the term 1 plus tan square theta to the power 3 upon 2 is also be extremely small, so we can neglect it. So exactly we did it here. We having the value of sec theta is equal to under root 1 plus tan square theta, and what we have here, sec cube theta. Okay, we put the value of this in sec cube theta, and we have d2y upon dx2 is equal to this value, 1 plus tan square theta to the power 3 by 2, and we neglecting this term, or we can say we neglecting the sec cube theta due to having a extremely small value, because it is in term of tan theta, or say in terms of theta, which is theta is very small. So after neglecting this term, we have d2y upon dx2 is equal to 1 upon r, and we already have the formula of bending stress of beam, where we can find the value of 1 upon r, which is m upon ei. So we have a relation for deflection of beam, which is a double differential equation or second degree differential equation, which is ei d2y upon dx2 is equal to mu or m. Here mu is denoted as a moment. Okay, then this equation is a double differential equation of moment for beams. Okay, now we get to start how many types to solve this double differential equation of moment of beam. So basically we have 5 ways to calculate this or to analyze this double differential equation to solve deflection or slope of any beam. So first method is double integration method, and second is Macaulay's method, third is moment area method, next strain energy method, and last one is conjugate beam method. So let's just discuss the first method, which is double integration method. As it is called double integration, which stating it is as by integrating it double differential equation two terms. Then we have a generalized equation, and as you can see that we already integrated double differential equation, and then we found this ei dy upon dx is equal to integration m dx plus c1, which is c1 is as a constant, and here the term dy upon dx is the slope of a curve at any point. And if we again integrate this equation, then we found this equation. EI multiplied by is equal to double integration of m dx into dx plus c1x plus c2, where c1 c2 are the constants. Then how can we solve this equation for any particular beam, for any particular loaded beam? So here is an example for that. We have a cantilever beam and load is placed at its end, one end. The length of the beam is small l, and then we cut a section at x distance apart from the end of the loaded area. So we can easily find the moment from x section, which is m is equal to wx negative because the moment generated for cantilever beam is always negative depending upon the type of the load is consisting. So let's just try to solve the equation. Then first equation is here ei dy upon dx is equal to integration m dx plus c1, and put the values. We integrated this value of m one time, then we have a minus wx square by 2 plus wl square by 2, which is a value of a constant which reduced by placing the end condition. Okay, then we can easily find the value of dy upon dx, which is w upon 2 ei bracket l square minus x square. Okay, here we again integrated this relation, and then we find the eiy is equal to minus w cube upon 6 plus wl square by 2x minus wl cube upon 3, and divided the whole equation by ei. Then we have a value of y. Now we have a equation for slope and equation for y, which is deflection. The only thing that left is to place the values, variable values, which is here is x. If we put the value of x is 0 or put the value of x is y, then we have a deflection and slope at two different points. So as you can see that we placing the value of x 0 in slope equation, then we have find the slope of the point or say section where x is 0 is this wl square upon 2 ei, by means this at which where load is applied, the slope is wl square by 2 ei, and when applying x equal to 0 in this equation of deflection equation, then we have a value of minus wl cube upon 3 ei, which means that at which the load is existing, the deflection is in negative direction, which is below the beam. The value of it is wl cube upon 3i, and according to which if we displace the load at any distance apart from the support, as you can see here, then again finding the moment equation, which is m is equal to minus w a minus x, and following the same procedure we can find the value of slope and deflection. As you can see that we analyze the two different points, which is y dash and yc, here by putting the value of x is equal to a by cutting a section at x distance apart. Okay, then we easily can find out the value of deflection at b point. We can also find the deflection at c point, which depending upon the limit of x, we can know that if x is equal to a, which is shown in here c point, the deflection at c point is denoted by this formula, yc is equal to minus wa cube upon 3. Okay, and if we want to find the deflection at b point, then what we have to do, which is calculated by this formula, which is yb is equal to yc plus y dash cb, and whatever the distance of cb is, which is total distance of beam minus a, and we place it here. Then yb is equal to yc, which is calculated here and place it here, and y dash, which is here, placed here, and cb, the value of cb is l minus a, and we solve this part and we get the formula for deflection at B point. So next method is Macauley's method. We can discuss this method in next lecture. Okay, thank you.